first off, I just want to speak about the cause of what has happened up here. These buildings were built back in the 80s. Back then, the building code wasn't as strict as it is today. It didn't take into account a lot of issues that we do today. And what's happened is that on the south and western exposures on all the buildings, there's been severe failure of the materials. And that happens because it's most exposed to solar rays, all the southern, especially all year round, and the western elevations are exposed, this time of year when the sun's setting up to the north. And so those two sides took the biggest beating of all the elevations. And with cedar, when there's a huge temperature swing of over 100 degrees, the material moves. And as the material moves, it slowly pulls apart and creates leaks and water gets behind it. On these buildings, that situation is made worse by the fact that all the buildings up to 6 and 7, there isn't plywood or sheathing on the walls. There's just a fiberboard called cellulose. It's a black material, fibrous, and it doesn't have any real structural integrity to it. And so what's happened is that you have an inch of this material, the structure of the building, the studs behind it, which are only 2x4s, 16 inches on center, and then they're nailing the siding onto that. So there's a 1-inch lever arm in there that nails are able to move up and down on. And between the thermal differentials that occur and the extreme winds that we have and the moisture being driven in and the freeze-thaw cycles that we have, the siding is really pulled apart. And if you walked around some of these buildings, you would see it, and I have pictures of all this stuff. And then once the water, so it's like a downward spiral cycle. As the water gets in, it creates more damage. As more damage is created, as the materials weaken, it gets worse and worse and worse. And and that's present on all the buildings, with the exception of the one that was built most recently. And that one was actually built up to the code of the time, requiring 2x6 walls and actual sheathing and things like that. So that's cause number one. And all that material on the southern and western walls, most of it is way beyond the point of repair. Standard life cycle for cedar, when applied properly, is around 25, 30 years, something like that. This stuff was not originally applied well. Back in the day, that's the way they did it, but it is not withstanding the test of time very well at all. And I think the maintenance people here have done a very good job in holding the buildings together. You can see on some of the pictures where they've been painting and fixing and doing stuff and doing the best they can, but they can't salvage it. It has to be replaced. On the eastern and northern elevations of the buildings, the material's in better condition. There's still problems with it. It's still attached the same way, but because it's not exposed to the extreme winds that we have up here and extreme solar gain and loss, and it just has withstood the test of time a little bit better, so it's not nearly as severe. If you look up at the chimney chases, they are all in very poor shape because they're completely exposed to the wind, completely exposed to solar, and they're just in very poor shape, and that material all has to be replaced. While we're looking, once we dug into the buildings, I opened a couple of test areas so I could ascertain what the problems were. Another issue is that on the outside exterior of the Celotex is a vapor barrier, visqueen, and that has no permeability whatsoever. So in the wintertime, what happens is the moisture inside the house is trying to go to the outside because it's just transferring through. The problem is that when it hits that vapor barrier, that visqueen, it has become a cold side vapor barrier. And that cold side vapor barrier, as soon as vapor moisture hits that, it condenses. And that's another moisture problem. And so whenever there's moisture in wood, there's decay. And so a lot of these areas, there's decay to some degree of the sill plates, but it's not horrible. I've seen much worse. I redid a hotel up on Mackinac Island a few years back, and we went in there and we told the clients that we have to explore and find out what's wrong with the building, and had to get their permission because said it's a public place, and if we find it's structurally unsound, we're gonna have to condemn the building until we could provide shoring. And of course, they agreed to it. We probed the siding, and our knives went right through it. And so we had to redo the whole thing, the emergency shoring and all that stuff. And that's when I found out why all the buildings on Mackinac Island are painted white. Because as I was working up there, I've done several buildings up there since then, they use white paint up there because, and I asked the painter, he said, well, it's Elmer's paint. I said, excuse me? Well, 50% Elmer's glue, 50% white latex. Those buildings are literally glued together. And that's something I hadn't known, and so I've seen worse than what you have. I've seen it up there, it's horrible in some buildings. But we salvaged all those buildings. But and so where we are now, so that's the cause and the discovery. It is pretty much, the buildings that were built first are in worse condition, as you would expect, and the ones that were built a little bit later are better, except for the southern and western sides, which are really in rough shape. And then you go all the way up top of the hill, 6 and 7, and they're built to better standards, and they're newer and they're in better shape. Back to the issue though, on the southern and western elevations, they're severe enough that what we wanted to do was pull, because we're getting moisture that's being driven in from the environment, and we get moisture from condensation, from water coming through from the inside. And and to manage that, what you have to do is create what we call a drainage plane. Because with only 3.5 inches to put insulation in, we can't get the R value to control what the dew point is. So I know there's going to be moisture, vapor moisture traveling through that wall to the outside. And I know there's no way that you can keep water out from a construction assembly in northern Michigan because of the things I've been talking about. So you have to sort of plan. You have to plan that there is going to be a failure, there is water going to get into the wall, so we want to wait for the water to get out. And so we created for you a drainage plane. And on the extreme elevations, the southern and the western elevations, I recommend that you use an actual air gap of 3/4 of an inch, ½ inch or 3/4 of an inch, so that there's actual air movement in there, so that as it gets wet, it's able to dry out. On the other elevations, we recommend that you just use excuse me, I can grab a sample here. I recommend that you use a mesh, use a mesh product like this, and you guys can pass it around, instead of an actual air gap. And this is another material, which is the infiltration weather barrier that's required. And so on the southern and western elevations, to control the problem, we're recommending that you take the fibers board off, the cellulose off the building, take the insulation out that's there because it's just fiberglass. It's 3.5 inches of really bad fiberglass, which provides very little thermal R value and almost no infiltration resistance. So we recommend on those elevations, the ones that are most damaged, that you go back all the way back to the back side of the interior drywall. Take everything out, and then as we build it back out again, we want to use blown-in cellulose, which is a very good product because it provides a higher R value per inch than fiberglass. It also has an antifungal in it, boric acid. And so there's no way that you're going to get any kind of mold, once this is installed. And then we're going to put on ½ inch CDX plywood, which will increase the strength of the building so it's not moving so much. And then on top of that, we'll put furring strips, first with the weather barrier, which is, that little sheet that I'm handing around. And then we'll put the siding on that. And that will allow for the best system to extend the life of the material. Because even though it's going to get wet, it's going to be able to dry out. The wood decays much, much quicker when you can't dry it out. The moisture just starts eating away at it, and all sorts of badness starts to occur. And since those are the most weathered sides, I recommend you have a real plan, a real drainage plan, to ensure that you don't have problems down in the future. The other elevations, the eastern and the northern ones, I hope I'm not confusing you guys, because it takes me a while. I get confused on this. On those elevations, what we're recommending is that you take off all the damage, take off all the cedar, replace that. We're not gonna take off the cement board, the cellulose. We will put on new infiltration barrier, and we'll be able to just put new siding on. But before the siding goes on, that mesh product I'm handing around will be put there. So that too is a drainage plan. That drainage, it doesn't allow as much ventilation as an actual 1/2 to 3/4 of an inch of open airspace, but it will allow some, and it will allow any water that gets in there to run out. So it will dry out. And that's really how we build things today, and have for quite a while actually. You have to plan that the surfaces will fail in northern Michigan. We have extreme temperature swings, we have extreme solar gain, and you guys have huge winds up here. And so this all contributes to what we have today. And what we have is